Okay. We are on our last section in chapter 10. It's our last hypothesis testing chapter, and then Tuesday we will do 12.1 and 12.2. Those two sections go together, and then we'll be finished with material. And the only thing that's different in this section is that instead of dealing with means, we're dealing with proportions. Okay, so 90% of the hypothesis testing that we're doing is going to be just like the other sections, especially this one's a little more similar to 10.2 than 10.3. We do have just a little bit of a tweak we've got to make. Oh, don't let me forget. I got the test. I can't let you keep them yet because everybody hadn't made taken their makeup, but I can let you look at them today. Okay, so when we get done with this, remind me, and I'll give those to you to look over before you leave. I took them to my last class and forgot all about it. So I had like 2 students left when I remembered. So, okay. So remind me about that. Okay, when we get done. This will be a short section, right? I had it planned to do on Tuesday, but we're having technical issues, so we just extend it out because we're in good shape in this class. We're not behind or anything. All right. Anybody think anything we need to talk about before we get into it? Anything? Okay. All right. So since we are working with proportions instead of means, we have to have a new formula for a test statistic because our previous formulas for test statistics involved means, right? They had means in the formula. So that's our first order of business here and the major difference. Okay. So just like with confidence intervals, when we're dealing with proportions, that's really binomial data. What we're going to do is we're going to use the normal distribution, because remember I mentioned if we have certain conditions, then the binomial distribution, we can use a normal distribution in its place. And we've got the conditions up here. Right? N times P needs to be at least 10. N times 1 minus P needs to be at least 10. I'm not going to try and trick you on that. We're not going to bother with checking it on these. But that is a requirement for us to use a Z. Okay. If you don't have these conditions, there are other formulas we can use. You can actually use the binomial distribution if you want to test for a proportion. Okay. We're not getting into that. So looking at the formula, it is, the top part is similar to our other formulas, right? But instead of X bar, we have P hat, sample proportion, instead of sample mean. And instead of mu, we have P, population proportion, instead of population mean. Okay. And just like before, for our population number, this time P, previously mu, this number we don't actually know, because if we did know P, we would not have to be doing a hypothesis test. And so what we use for this number in the formula is we use the number in the null hypothesis. Okay. So just like with mu, that number that was in the null hypothesis, P will come from the null hypothesis as well. Okay. And that goes in 3 places in our formula. Okay, so this P, and this P are all from the null hypothesis. This is always a 1. So the only other 2 numbers we need the sample proportion, P hat, and we need the sample size, N. That's everything we have in there. So we have to have slightly less information in our formula here. Okay. Some tables. Okay. There's our formula. Go. Look. Okay, and that's our major difference. Pretty much everything else we've seen, okay, whether in 10.2 or in 10.3. Okay, so since we're using a z test statistic, finding z, that means we can go back to using p-values, which is the more common method for making a conclusion. So here's our rule. This is just like a slide we had in 10.2, so it's nothing new, it's just a reminder of our rule. We compare our p-value to our significance level alpha, and if p is less than or equal to alpha, that's when we reject the null hypothesis. Or if p is greater than alpha, that's when we fail to reject the null hypothesis. And a reminder on finding p-values, and it's been a week. If we're doing a left-tailed test, our p-value is the area to the left of the test statistic. If we're doing a right-tailed test, our p-value is the area to the right of the test statistic. And if we're doing a two-tailed test, then we consider the negative and positive version of our test statistic, and we want the area in the left and the right tail together. Two tails in that case. So that's just a refresher. And then one thing to mention to be careful of, you'll notice hopefully that whenever I write down p-value, if I'm labeling something as a p-value, I always write out p-value instead of just using p. One reason for that is that here with proportions it can get confusing because we use p for proportion, and then if we have another p it gets confusing. So I always write p-value, okay? And then p, two different things. That is why some authors use pi instead of p for proportion. So we don't have so many p's floating around there. Okay, well, we're ready to do our hypothesis test in this section. Okay, I've got one of each type. I've got left, right, and two-tailed. And we'll be done with chapter 10. Okay. So let's take a look. Look at our first one here. It says the local school board has been advertising that 65% of voters favor a tax increase to pay for a new school. The local politician believes that less than 65% of his constituents favor this tax increase. To test his belief, his staff asked a simple random sample of 50 of his constituents whether they favor the tax increase, and 27 said they would vote in favor of the tax increase. If the politician wishes to be 95% confident in his conclusion, does this information support his belief? So just like in the other sections, we need to get started by coming up with our hypotheses. So we need to know what claim we're testing. So here we want to test the politician's claim. And if we back up in our information, it says the local politician believes that less than 65% favor the tax increase. Here we're dealing with proportion instead of a mean. So we're not going to have mu, we're going to have that p is less than 65%. Okay? It's going to be our alternative hypothesis, that p is less than 65%. And to make it easier on ourselves in our calculator, we'll change it to a decimal. So HA, alternative, that p is less than 65% or 0.65. And the way we're writing our null hypothesis will be that p equals 0.65. There's step one. Step two, we have to figure out which formula to use. That's going to be easy in this section, and because if we're dealing with proportions, we're only going to have one formula. So for proportions, we're going to use the only formula we have for those, the z for proportions formula. So we do have two z formulas, and we want to use the one that has the proportions in there, not the means, if we're dealing with proportions. And we also want our significance level. Okay, so if we go back to our problem, this one does not directly give us significance. It's thinking about it the other way around. It says if the politician wishes to be 95% confident, so we have to do 1 minus that number to get significance, alpha. So 95% confidence means alpha is 1 minus 0.95. That's our confidence level. So alpha is 0.05 or 5%. Okay. And step 3 is where the majority of our new material is. We're using our new formula. Step 3, I'm going to fill into our formula. Here it is again. P hat minus P over the square root of P times 1 minus P over N. So P, we already have the number for, because P is going to come from our hypotheses, just like mu did before. Okay, so for P, we're going to use 0.65. And that goes 3 places in our formula. Okay, so we'll subtract 0.65. And then in the bottom, we have 0.65 times 1 minus 0.65. The only 2 numbers we're missing the sample proportion, and we're missing our sample size. So going back to our problem, oops, sorry. Going back to our problem. I see, this is just not a good technology day. Let's see. Yep. I don't know why flipping it unfreezes it, but it does. Going back to our problem. There we go. If we read through, it says we have a simple random sample of 50. That's our sample size N. And then for P hat, well, we need to calculate it. And you remember P hat is X over N. We don't always have to calculate P hat, but this one doesn't give it to us directly. So X is just the number of data values we're counting that has whatever characteristic we're counting. N's our sample size, which will be 50 here. This one, we want to count the people that favor the tax increase. So how many of those do we have? We have 27. So P hat will be 27 over 50. Okay. And I think usually Hawks will let you round these to 3 decimal places. So in real life, okay, this is really our data and we really want to know the outcome. We would keep as many decimal places as it gave us, okay? Because we would be doing this in software and we would just let the computer keep up with it. If it was something that didn't end, I don't know how many the computer keeps, 20, something like that. Okay, more than we would ever need. But here, if we do 27 divided by 50, oh, this one comes out 9, so I was thinking about the next one, I guess. Okay. So this one we get 0.54. And it's P hat. Okay. So now we can fill into our formula. So P hat's 0.54. N is 50. Then we can type this thing into our calculator. So what I typically type in on these is, let me get a different color here. I would put, if we're doing it all at once, okay, I would do parentheses 0.54 minus 0.65, close parenthesis, divided by, we've got to do the fraction bar, and then square root. Most scientific calculators, that comes with a parenthesis already. And 0.65 times 1 minus 0.65. And then divided by 50, close parenthesis, and then equals. Let's see what we get there. So rounding to 2 decimal places because we're using a z here. I get negative 1.63. You may try to having calculator issues. Okay. So then almost done. Step 4, I need p-value. So for our p-value, we need some other information. So we need to know what type of hypothesis test we're doing. Is it left-tailed, right-tailed, or two-tailed? So what kind is this one? Yeah, less than points to the left. So we're looking at our alternative hypothesis. So this is a left-tailed test. So for our p-value, we want the area to the left of our test statistic. So we want the area to the left of negative 1.63. So to get that, we just look up negative 1.63 on our z-tables. And let's see. Negative 1.63. I get 0.0516 for my p-value. Okay. All right. So now, final step, we're going to compare our p-value to alpha, which is 0.05. You don't have to write it all down again. I just like to. So I'm going to say my p-value 0.0516. Alpha is 0.05. So in this case, the p-value is a little bit bigger. So if the p-value is too big, if it's bigger than alpha, you remember what our conclusion is? Fail to reject the null hypothesis. It was close on this one, but that's our decision. Again, remember, it's a weak statement. All we're saying is there's not enough evidence in our data to support, in this case, the politician's claim. In real life, if it's that close, then maybe you need to go out and collect some more data and you'll have stronger evidence. You might not, but worth checking. Here, that's all we can do. Follow it, yeah. Because it's in steps, right? So like, so state the hypotheses. I'll need these. That part kind of comes along on its own, but there's one that will say, what's the level of significance? Give me that number. One will say, calculate the test statistic. That's this number. One will say, find the p-value. That's that number. And then they'll say, what's the conclusion? So that's this. Yeah, it's step by step. Alright. Other questions on that one? This is the first time for almost everybody to see hypothesis testing. It would be almost to the point of cruelty just to get you to give me the final thing. Okay, because that's a lot of steps to make it through without making a mistake. Yeah. Okay, that's our first one. Well, we got two more just to get in some practice, I guess. So I left all the textbook stuff in the slides if you want to read through any of that. They check the conditions also. Okay, we're just not bothering. All the ones we're going to do meet the conditions for using the normal distribution with the proportions. You see that going on, that's what they're doing. Okay. Next one, this one's a little wordier, but it's kind of interesting too, so worth it. Okay. So we've got information that researchers in an Apple funded study reported that 0.5% of participants received irregular pulse notifications, indicative of possible AFib or atrial fibrillation from their Apple Watches. So people's Apple Watch telling them their heart's not beating correctly. To improve the benefits of pulse notifications, it's important to identify the percentage of people receiving false notifications. Okay, so now most of the part we care about is here. Okay. Suppose that a cardiologist is concerned that the reported percentage of people receiving these notifications is not accurate. To perform the hypothesis test, the doctor conducts a simple random sample of 2,315 people in the area who own Apple Watches and ask if they have received a notification of an irregular heartbeat. 9 of the respondents claim to have received such a notification. Does the evidence support the cardiologist's claim that the percentage of people who receive notifications of irregular heartbeats is not 0.5%? We're going to use a 0.01 level of significance. So the doctor just wants to check this number put out by Apple. So his concern, his claim that we want to test is that the percentage, or claim that the percentage of people who get these notifications is not 0.5%. Okay? That's what we want to test. So when we write down our alternative hypothesis, we're testing the claim that the proportion is not, it doesn't say more, it doesn't say less. So what should we use? Not equal to 0.5%. To make it easier on ourselves and our calculators, we need to change that to a decimal. So as a decimal, that would be 0.005. So our null hypothesis would be that P does equal 0.005. Step 2, we're not gonna beat it to death, but we're dealing with proportions, so that's all I'll say. We'll use our formula that involves proportions. We only have one. And then for our significance level, this one was a little nicer. It just gives it to us. And even though it is down at the very bottom, it says use a 0.01 level of significance. That's alpha. So 0.01. Okay. Step 3, we'll calculate our test statistic. So P hat, P hat minus P. Oh, I know P already from our hypothesis. I'll go ahead and fill it in. So we need p hat, sample proportion, and we need n, the sample size. All we're missing. So on this one, it says to perform the hypothesis test, the doctor conducts a simple random sample of 2,315 people. That is n. And to get our sample proportion, we need to know how many of them got these notifications. Those are the ones we're counting. All right, so here it says 9 of those got the notifications. Okay, so for p hat, I'm gonna put it down here. And for p hat, that's 9 out of 2315. And if you're doing these by hand, okay, you'd want to keep a bunch of decimal places here, kind of like we do a margin of error. So the textbook would say keep 6 decimal places here. But I think in Hawks it lets you round to 3 decimal places, so we'll just round to 3, be a little bit lazy. Do 9 divided by 2315. That gives us 0.004. Again, in the real world, okay, if you're doing this in some software, the computers are going to keep up with a whole bunch of decimal places for you. So we've got our number. We got p hat and n. So 0.004, and n is 2315. Now we get to punch this into our calculator. So on this one, I got, let's see if that's close. I got negative 0.68. Hang on, let me try that one more time. Anybody else get that thing? That's what you got? Okay. That's because we're rounding, so. All right, we'll go with it, okay? So we're gonna be a little bit different than what the textbook stuff's got in these slides because we round, but it's okay. We'll get the same result. Okay. Then for the p-value, this time we are, okay now, doing a two-tailed test because we have not equal to. So when we find our area, get our p-value, we're not only concerned about our test statistic negative 0.68, we're also concerned about the value on the other side, positive 0.68. We want the area in both of these tails. So the short way to get to that answer is we can do 2 times the area to the left of negative 0.68. So that'll be 2 times, what do we get there? I'm looking at negative 0.68. I get 0.2483. When we multiply by 2, our p-value is 0.4966, which is huge for a p-value if you're trying to reject the null hypothesis. So then we compare our p-value to alpha, which was 0.01. So our p-value was 0.4966. Alpha was 0.01. P-value is much bigger on this one. So what's our conclusion? Yeah, we failed to reject the null hypothesis. P-value is too big. Okay. So if we rejected the null hypothesis, there's almost a 50% shot that we've made a type 1 error. We don't want to do that. Failed to reject the null hypothesis. Okay. Questions on that one? Okay. So if you let's look at the textbook numbers. They kept 6 decimal places, so their test stat and p-value turned out a little bit different. And they get the same result on this one because it's so extreme. Let's look. So for their p-hat, they kept 0.003888. Okay. And then when they plugged that in to the formula, they got negative 0.76. And for their test statistic, which made their p-value, I'm at 0.4472, but they get the same conclusion at the end. And I'll tell you if it's one, well, probably what will happen is on test time, it'll just be a p-hat will just come out to a nice smaller number like the first one. Yeah, where we had like 0.54, something like that. That way you don't have to worry about it. In real life, you can see just our rounding. Okay, so just rounding to 3 decimal places instead of 6 really changes the p-value there. So that's why in real life we keep a bunch of decimal places, right? So computer would keep, I don't know, like 20 decimal places for us, okay, if we were doing it in software. Okay. All right. Okay, last one. And you get a little break till we do our test review. So it says, according to the International Telecommunications Union, 75.23% of people in the United States were using the internet in 2017. And that reminds me, one moment, please. Let me stop